Hello, I am going to deal with single degree of freedom system in structural dynamics. Let us see a problem of a simple frame. A steel frame is fixed at the base and it has a rigid top having weight 455 kg. It was found experimentally that its natural period T in lateral vibration is 1/10 of a second, that is 0.1 second. Now, it is required to shorten or lengthen its period by 20% by adding the weight or by strengthening the columns. Now, the question is determine the additional weight needed or additional stiffness to be provided, and we have to neglect the weight of the columns, two columns. So, here this left diagram shows the frame, whereas the right diagram is analytical model or mathematical model of single degree of freedom system, where spring constant K represents the stiffness of the system and mass M is nothing but the mass of the system and U is the displacement. Now let us begin. Now we know that angular frequency or circular frequency omega is given as 2 pi by time period, which is again equal to square root of K by M, where K is the stiffness and M is the mass. We know that weight W is mg and therefore it becomes square root of kg by W. Now again, since W is mg and the mass at the top is given as 455 kg, so let us convert it in weight. So it becomes 455 into 9.81, that is 4463.55 Newton. Now again substituting in this formula, 2 pi divided by T is 0.1 seconds because it is 1/10 of a second is equal to K into 9.81, that is K into G into 1000, because 9.81 is meter per second square, we want mm per second square. So we are multiplying by 1000 because 1 meter is 1000 mm, divided by already W is given, that is 4463.55 Newton. So square root of that. Now when I solve, I get stiffness of the system as 1796.268 Newton per mm. Now let us go for case A. That is, I want to lengthen the period by 20% and therefore TL is equal to 1.2 into 0.1 second, because we have to lengthen it by 20%, so I have to multiply 0.1 second by 1.2, so that becomes 0.12 seconds by adding weight delta W. Now when I substitute this, it becomes 2 pi by 0.12 is equal to, we know that K is 1796.268 into G is 9.81 into 1000 divided by, now instead of W it will be W plus delta W, because I am trying to lengthen the period by adding some incremental weight. So it becomes 4463.55, which is already given in the problem, plus delta W. So square root of that. Now when I solve, delta W is equal to 1963.96 Newton. This practically means that when I want to lengthen the time period of the system by 20%, that means instead of 0.1 seconds, when the time period has to be 0.12 seconds, then I have to add the weight at the top as 1963.96 Newton. That means originally the weight was 4463.55 Newton, and again to that I have to add the incremental weight of 1963.96 Newton, so that the period lengthens by 20%. Now case B, we have to shorten the period by 20%. So it is 0.8 into 1/10 of a second, that is 0.8 into 0.1, that is 0.08 seconds. How we do it? By strengthening the columns in delta K. That means we are increasing the stiffness of the columns. That is called a strengthening of column. Again we use the same formula, that is 2 pi by T is square root of kg by W. Here 2 pi divided by T is 0.08 seconds is equal to, again our K is 1796.268 from here, plus delta K, because now it is not only K, we want to strengthen the columns, both the columns, by increasing the stiffness. So the incremental stiffness is delta K. So instead of K, it becomes K plus delta K into G is 9.81 into 1000 divided by W as it is, that is weight at the top, 4463.55 Newton. So square root of that. So delta K is 1010.4 Newton per mm. So it practically means that when I want to shorten the period of the system by 20%, that is instead of 0.1 seconds, if it has to be 0.08 seconds, then I have to strengthen the column, and strengthening the column means I have to increase the stiffness, and initially the stiffness was 1796.268 Newton per mm, and now I am adding the stiffness by 1010.4 Newton per mm to get the more stiffness, so that we can strengthen the column. Thank you very much.